Welcome to Chapter 3, Section 3, Techniques of Differentiation. Or in other words, we're going to look at some shortcuts today on how to differentiate. So, in the last section, we learned how to differentiate using the limit technique, which will work for any and every function. However, it can get a little cumbersome and a little long when you're dealing with higher order polynomials or functions that are a little more difficult. So, we're going to look at some things that we already know, some things that maybe you noticed when using the limit form. For instance, when taking the derivative of a constant, so say c is just some constant, say it's a number like 5, and we want to take the derivative with respect to x, well, this is asking how much is this function changing with respect to x? Well, if it's a constant, it's not changing at all, so therefore its rate of change is 0. And we can confirm this graphically if we look at what does y equals 5 look like. Well, it's a horizontal line at y equals 5, and we know the slope of that line is always and forever 0. So this is a rule that we can put in our back pocket, knowing that the derivative of any constant is always going to be 0. Now, let's take the derivative of a variable with an exponent. And what this is telling us, the derivative of x to some power of n with respect to x is always going to equal n times x to the power of n minus 1. What that means is if you have x to some power, so let's say we have x to the third power, and we want to take the derivative of that with respect to x, well, that's simply going to equal, we take this exponent 3, and it becomes a coefficient. And then we decrease that exponent by 1, so 3 minus 1 is 2. So the derivative of x cubed is simply 3x squared. So instead of having to expand the binomial x plus h to the third power and doing the limit, subtracting f of x and dividing by h and the limit as h approaches 0, we can just jump right to x cubed, the derivative of that is 3x squared. So something like x to the 7th, the derivative with respect to x, is simply 7x to the 6th. So those derivatives can be done very quickly and very easily. One other thing dealing with a constant, if we have a coefficient, constant coefficient, that can be taken out of the derivative. Just like we could take constants out of limits and put them out front, well, the same thing happens with the derivative. A constant times a function is the same thing as that constant outside of the derivative of that function. So let's take a look at an example. The derivative with respect to x of the function, let's say 4x squared. Well, that's the same thing as saying 4 times the derivative of x squared with respect to x. And we just learned with our power rule back there that this is just going to be 4 times 2 times x to the first power, and we don't have to write it because x to the first we can just leave as x. So this simplifies to 8x. So the derivative of 4x squared is simply 8x. Now, we also can look at the addition of functions and the subtraction of functions. When we take the derivative of a sum or a difference, it's the same thing as taking the sum or difference of the derivatives of each individual function. So how that works for us, say we have a function 3x squared plus 2x minus 4, and we want to take a derivative of this with respect to x. So it's the same thing as taking the derivative of just 3x squared and taking the derivative of 2x and taking the derivative of negative 4 and adding all those together. So we can look at the derivative individually for each of these pieces. So we know the derivative of 3x squared is simply 6x because the 2 comes down as a coefficient. 2 times 3 is 6. X to the 2 minus 1, well, that's just x to the first power. And then plus 2. Now, what happened to our x here? Well, we have an exponent of 1. That becomes a coefficient. 2 times 1 is just 2. And then 1 minus 1 is 0. So we have x to the 0, meaning it's not there. And then the derivative of negative 4 we know is 0. So the derivative of this function here is simply 6x plus 2. So instead of going through all that long process with the limits, we can take this polynomial function and end up with its derivative quite quickly. Now, there are two rules that we're going to look at here. called the product rule and the quotient rule. And they get a little more involved, but still not as bad as what you may think. So first, the product rule tells us that if you have a derivative of a product of functions, that's equal to the second function times the derivative of the first plus the first function times the derivative of the second. Now, your book actually has this reversed. It has this term, the f of x times dgx dx, listed first. It doesn't really matter because of the commutative property of addition. I chose to list it this way because of the rule that's coming after this, so that way they're in the same type of format. Either way you write it, whether you have the g of x listed first or the f of x listed first, it doesn't matter. They're still the same thing. So let's take a look at an example here. Let's say we have the function 3x squared plus 6, and that quantity is being multiplied by the quantity x minus 2. And we want to take the derivative of this with respect to x. Well, what this rule tells us is we can simply take the second function, x minus 2 in this case, and we're going to multiply it by the derivative of the first function. Well, if we look at this, we can take the derivative of each piece individually, and 3x squared, the derivative of that is 6x, and the derivative of 6 is simply 0, so it's just 6x. And then we want to add the first function, 3x squared plus 6x, and we want to multiply by the derivative of the second. Well, the derivative of the second, we just have 1x. We keep the coefficient of 1, and derivative of x is simply just 1. So we can look through here and see that, well, let's combine like terms. We get a 6x squared plus 3x squared gives us a 9x squared, and then a negative 12x, and there aren't any other x's over here, so that's minus 12x, and then we get plus 6. And so the derivative of our function here is simply 9x squared minus 12x plus 6, using the product rule. So anytime you have two functions multiplied together, you can follow this product rule. Now, all these rules that I've given you so far, I can derive them for you analytically and graphically. There are some derivations in the book. I'm not going to take the time to do those here in the video, but if you're interested, you can either ask me about it in class or take a look at how the book explains it for you. Now, the last rule I want to take a look at here is the quotient rule. So when you take the derivative of two functions that are being divided, and we have a top function in our numerator and a bottom function in our denominator, it follows this rule that we have listed here on the screen. And if you notice, it looks very similar to the product rule. Actually, the numerator is just one sign away from being the product rule, in that we have the derivative of the second function, the second function times the derivative of the first function, but now we have minus the first function times the derivative of the second instead of plus. So we want to subtract, and all of that is over the denominator squared. Okay, so this is the rule that we have to follow anytime we have a product of functions that we want to take the derivative. So let's look at an example here. Let's say we want the derivative of a function, and let's have x squared minus 3x all over x cubed plus 4. Okay, here's our function, and we want to take the derivative of that with respect to x. So what this tells us is that we take the bottom function, x cubed plus 4, and we multiply it by the derivative of the first, which in this case is going to be 2x minus 3. Now, once again, let's review. Where do we get the 2x minus 3? 2 comes down as a coefficient, decrease the power by 1, so that gives us just an x. We keep the coefficient of negative 3, decrease the power by 1, get a 0, so we're just left with a 3. And then we want to subtract the numerator function, which is x squared minus 3x, and we want to multiply by the derivative of the bottom. Well, that's going to give us a 3x squared. Now, what happened to the 4? Derivative of a constant is gone. It's 0. Okay, now the bottom is simply just g squared. We want to square that bottom function, and in this case that'll give us an x to the 6th plus 8x cubed plus 16. Okay, that's just expanding the binomial of x cubed plus 4, quantity squared. So when we distribute and we simplify and combine like terms, this simplifies into a negative x to the 4th plus 6x cubed plus 8x minus 12 all over our denominator of x to the 6 plus 8x cubed plus 16. Now, we can't simplify this any by factoring or anything like that, so we just leave it as this quotient right here. So, as you can see, that helps us take the derivative of a function that in the limit process would have been almost impossible. It would have been possible, but very long and tedious in order to do this using the limit technique. And it made it able to be done in a few short steps. Now, what I want you to do is I want you to take a look on page 197, and I want you to practice a couple problems here for me. I want you to try number 1, 4, 6, 18, and 22. And once again, that's on page 197. One quick little reminder here. If you happen to see something like a radical x, it may help you to write this as x to the power of 1/2. Because when you take the derivative of that, well then the derivative of x to the 1/2 dx, that is simply 1/2 x to the negative 1/2. Or in other words, it's 1 over 2 radical x. So you may want to remember to write everything as rational exponents, or in other words, if you have something like 1 over x squared, that is also x to the negative second. And why do we want to write this as x to the negative second or x to the 1/2? Well, because then you can use your rule of x to the n. When you take the derivative, you get n times x to the n minus 1. So give those 5 problems a shot before you come into class tomorrow, and we'll continue learning some more techniques of differentiation.